Oh, wow. Okay. All right, everyone. Welcome to the AAAFM UCLA 2021 conference. This is session FCM-4, Functional Composite Materials. A few things. I'm the chair, Shirley Tan from the University of Waterloo. My main goal here is keep the time. Limit your talk within 10 minutes. And I will give you a reminder at the end, about 30 seconds to your time limit. If you have a question, you are encouraged to contact the speaker directly. And also, if there is time at the end of the talk, you can raise your hand, and then I will unmute you for asking the questions. All right, let's get started. Our first speaker is Jinghong Yep from Tokai University, Japan, about porous PDMS membrane prepared by phase separation method and its applications for cell culture. Jinghong, please take the stage.
Okay, I'm sharing the PowerPoint now. Okay. Greetings, I'm Yap from Malaysia, and I'm studying at Tokai University, Japan. I wanted to present our research title, Thin Porous PDMS Membrane Prepared by Phase Separation Method and its Application for Cell Culture. So start with the introduction and background. So the microphysiological system, MPS, such as the diagram here, consists a promising tool for studying the organ interaction in vitro. And the MPS with the porous membrane integrated, such as the diagram here, are useful for studying cells biology. The common cells culture membranes are made from polyethylene terephthalate, PET, and the polycarbonate, PC, both of which are rigid polymer and are not appropriate for cells that require a deformable membrane, such as lung and the gut cells. Also, the PET and the PC membrane would tear after applying pressure on it, as the diagram here shows. Furthermore, the porosity of PET membrane having a low porosity, and the PC membrane is a semi-transparent, which is causing the difficulty of cells observations. This means a soft and a deformable high porosity membrane is needed. The previous research showed that a PDMS porous membrane was made by using a polymer, as the diagram here showing. However, the cells in the device were poured into the blood sign channel, as the diagram shows here, with the 10 micrometer pore size. Moreover, the membrane still having a low porosity, which is 4.62%. Next, the PDMS porous membrane preparation in this research was using the phase separation method by using the spin coater. The porous structure will induce by evaporating the solvent with the high-speed rotations, as the diagram shows here. Our research aim was to fabricate the PDMS porous membrane by using the phase separations. The requirement of the porous membrane will be 1 micrometer to 10 micrometer of membrane thickness. The higher porosity, a smaller pore size below 5 micrometer, which causing most of the cells will not pour into another channel. And the most important is the cell's culturability. The material used in the fabrications was the polydimethyl siloxanes, PDMS, the molecular weight 800 to 5,000 polystyrene, and taurine. The membrane solutions was mixed with a different weight ratio of each material. The first, create a PVA sacrifice layer on the silicon substrate, then add the mixed solutions on the substrate and spin in at 7,000 rounds per minute. After that, bake in the 85 degrees Celsius oven for 24 hours. Second, dip the membrane into the torrent to melt the polystyrene on the membrane after bake and to form a porous structure. After that, attach the cell culture insert on the membrane with the non-toxic double-sided tape and dip into the water to dissolve the PVA. And finally, a Pdms integrated cell culture inserts will complete, was like a diagram shows here. So the different weight ratio of membrane was showing here. The right top column shows the weight ratio of, the right top column here showing the thickness of the membrane. And then the top chart showing the weight ratio of the high or low polystyrenes. And the left side shows the weight ratio of the torrent. So with the changing of the torrent, from the lower of the torrent weight ratio in the mixture, the membrane will become unstable and unable to form a proper porous structure, as the diagram shows here. Here's showing the porosity and the average pore size of different weight ratio membranes. So the membrane 1.5.10 here showing the it got the highest porosity. However, the handling was difficult due to his 630 nanometer thickness. So the membrane's 1.7.5, 7.5 has the second highest porosity, and he says 2.02 micrometer thickness, which is capable of handling. So the membrane 1.7.5, 7.5 was chosen for the rest of the experiments. Next, we made a hypothesis that the porosity affects the speed of diffusions. So we choose the rhodamine 123 and dextrons to test the rate of the diffusion of the different porous membrane, such as the PET membrane, the 0.64% low porosity, and the polycarbonate membrane with the 18.5% porosity, and the Pdms, our Pdms membrane, 12.93% porosity. So the fluorescent substance was mixed with the PBS, and then the concentrations of the solutions was the rhodamine 123 was 3 micromole and dextran was 1 micromole. The diffusion times was 24 hours from epiglots to the vessel. So in the result, the rhodamine 123 shows that they did not have any the diffusion rate did not have a high difference, but the dextrons shows that the higher porosity and the faster the rate of the diffusions. Moreover, we make a 6 stress test comparison of the PET membrane and the Pdms membrane. The stress test was tested on the water surface, such as a diagram here, to prevent the membrane bending. And the experiment shows, the experiment setup shows like that. The membrane is like stress testing on the water. So the puller here will pull the membrane and record the stress and the strains. And then we can just use the stress and test the strains to calculate the Young module. The lower of the Young module value, the softer the mercurial. So the Young module from the PET membrane was the 1,000 times 100 greater than the Pdms membrane from the result below. As you can see, there's the PET membrane is having the gigapascal Young modulus, and the Pdms was having the megapascal. And furthermore, the Young modulus between the porous versus non-porous Pdms membrane was not that statistically significant from the results. Next, to test the cell's culturability of the Pdms porous membrane, the Capacitor cells was chosen for the experiment. The seeding density was a 1.10 power 5 cells per centimeter square. The collagen 1P was used as an extracellular matrix for the cell culture. The graph below showing the TR of the cells populations. The cells will going well as the TR value increases. And the diagram on the right side shows the cells populations from day 0 until the day 21. Conclusions. Our research was the thin porous Pdms membrane prepared by the phase separation method and its application for cell culture. So the discussion of the research was the Pdms porous membrane can be adjusted by changing the weight ratio of each material. And then the polystyrene distributions could be disrupted by the concentration of the solutions. Then the porosity affects the diffusion speed on the high molecular weight material. And last, the most important things that our Pdms membrane has a cell culture ability. So we made a comparison of the Pdms porous membrane between the previous research. So we achieve a higher porosity and a smaller pore size, which means the Pdms porous membrane made by using the phase separation method can be applied to the cells assays. Thank you.
Thank you, Jinghong. Perfect in time. Our next speaker is Aranzazu Sierra Fernandez from Johns Hopkins University, US, and the Geoscience Institute, Spain, about bio-inspired lacquering-like composites as the next generation of materials for safeguarding stone heritage. Are you here, or we're going to play a video?
I don't have the video from this speaker.
You don't?
Yeah, I don't. I don't think they uploaded the video.
Okay, do we have the speaker here? Let me see. I don't think I see the speaker here either. Okay. So does that mean we just don't have the speaker? Yeah, I don't see anything on the job box either.
I also don't have the video from the third and the fourth speakers.
Okay, let me double check. Okay, so we don't have the second one. Let me see. I don't think we'll have the third or the fourth. Let me call the speaker then. Bing Xu, are you here? I don't think so. All right, so usually how do we do this, Chi-Ching?
So we can wait until say 4 p.m. to start the speaker. So what do you think?
Okay, so I think it's good to keep the time schedule, because I suspect some speakers will come only later when their presentation time is here. So we're at 6:35 here. Oh, actually, that's my Eastern time. I'm in around Toronto area. Okay, so we have so it's a 3:35. Let's come back at 4, because we do not have two of the speakers here to present.
Okay.
Okay, so anybody has, how can I see the chat? Because they are all muted, right? What if they want to speak? Oh, Deb. Oh, Deb is here. Okay, so your presentation is at 4 o'clock. Let me see. There. All right. Let's regroup at 4 p.m. Let's take a break and come back at 4 p.m.
Mm-hmm.
All right. Chi-Chen, I did receive an email from Fernandez saying that he uploaded a video.
Let me check.
It's the bio-inspired nacre-like composites.
Why? No, I couldn't. I didn't see the video.
Mm.
Yeah, it's not in the Dropbox.
Yeah, he did email this morning saying that he uploaded.
Okay. Hi, Dr. Peng.
Yes?
Yeah, I think we have a speaker ready.
For which presentation?
For the third one, the multifunctional bioactive hybrid lantern.
Okay. So this one is scheduled to be 3:40. All right. Can you? Oh, I see. Okay. So I didn't see. So this is Erhan in place of the presenter. Is that correct?
Okay. Yes, please.
All right. Welcome, and please take the stage and start your presentation. Yes, we can see your PowerPoint.
Okay, thank you very much. This is Erhan Pişkin, Emeritus Professor of Hacettepe University Chemical Engineering Department, one of the authors. Dr. Ferzane Muqteder, I am in Los Angeles now, so considering the time difference between Turkey and here, 10 hours, we decided maybe some internet connection, we decided that I can present a study on behalf of Ferzane Muqteder and two other co-authors, Erdal Karaöz, Yasuo Katabata. You can see the picture on the slide, her picture. She's originally a macrobiologist from Iran, working in Turkey more than 10 years. She is our R&D manager of Nanobiomedtech now. She recently moved to another company beginning of this month. She did PhD, Master of Science and PhD at Hacettepe University Nanotechnology, Nanomedicine program. I was her supervisor. Erdal Karaöz, the third author, is from İstinye University. He's the president of the university. Ferzane Muqteder did the second degree there on stem cells and tissue engineering program. This presentation related with this degree, so I'm gonna summarize what she have done. Professor Tabata is from Japan, Kyoto University, one of the leading scientists in biomaterials. She was able to work with him last year, about 1 year, and learn the techniques she was using in her degree thesis. Our target is to develop biohybrid tissue engineering materials for combined therapy of several infected wounds, including diabetic foot ulcers, accompanying with important amount of tissue losses and scar formation that are very difficult to heal. What we do is, our proposal is rather new. I don't know what we cannot see the picture here. Okay. Maybe, oops. I don't know, we have problems. Melis, we cannot show the pictures.
Cannot show me? Ne yapayım?
Şekiller çıkmıyor şurada.
Yapacak bir şey yok. Şeysiz anlatacaksın, şekilsiz.
Sen mi diyeyim? Okay, now it's okay. We have the figures. Yeah, I can continue. Sorry about that. This is the outcome of the study. We are producing biohybrids for combined therapy of infected ones, which is new. What you see here is not to scale. We have gelatin beads, and we load phages, the blue ones, and also BFGF, basic fibroblast growth factor, within these gels, microspheres, and then agglomerate these gels with mesenchymal stem cells and form agglomerates, 3D structures for the therapy, and phages for antibacterial effect, and the others, BFGF and cells for the regeneration of the lost defected tissue. Why it is important? Because normally in the treatment of infections like DFU, the basic methodology is using antibiotic therapy. However, the number of antibacterial resistant bacteria is increasing. It's not easy to fight with them. So we need alternatives to antibiotics. phages are the most abundant living organisms in the world, which are typical viruses, but these are not like coronavirus. They destroy specifically, only specifically infect and destroy the target bacteria. Therefore, they are our friends. They used pathogenic bacteria as the host to increase their number. They were invented more than 10 years ago, but forgotten because there were production of antibiotics strongly affecting all infection. But because of the problem, this antibiotic resistance, phages are getting attraction again very strongly. We're using here T4 phages, which is very well known and very well characterized. E. coli is its host, the target. As you see on the left, phages are accumulated on one E. coli. What they do, they just recognize specifically with their tail ends, the proteins in the tail ends. They sit on it and drill the bacterial wall and send their DNA within the cell. And this, in this circle, it's unbelievable, but it's only 20 minutes. After injection and the release, they kill the lytic, these are lytic phages, T4, and they kill the bacteria and come out, and their number is around 300, from one phage to 300 phage in 20 minutes. It's unbelievable. It's not comparable with any antibiotic effect. They have been already used in Eastern countries, Russia, Georgia. In pharmacies, you can find the cocktails you can buy and use. In the Western countries, not allowed yet, but it will come out shortly, most probably. They use, in this study, they use treatment of diabetic foot infections. They were successful, but you see, there's a huge scar formation, not good regeneration. So that's why we propose this new approach, combined therapy, using phages together with stem cells and some bioactive molecules like BFGF for triggering the angiogenesis, etc. These were, we bought both cells, bacteria, E. coli, and T4 from ATTC, and increase their number, and they will be that we can use. There are some pictures about these bacteria and phages. As carrier matrix, we use gelatin. Professor Tabata's group is well known with the gelatin microspheres. They are using for a long time, not for phages, but for other purposes. It is a biodegradable, bio-based polymer. It is obtained from native collagen, connective tissue polymer. It's a polypeptide. What we do, we just buy 100 kilodalton molecular weights. We use here basic and acidic gelatin for different purposes. I'm going to explain. What we do is we just form gels in oil phase from the gelatin solution, then cross-link them by using different techniques. Here we used glutaraldehyde as a cross-linker. These are some examples of the gelatin macrospheres. We can produce any size, but we selected the size between around 40 micron, which was quite suitable for stem cells. And the swellability was of these glutaraldehyde cross-linked particles in water is around 93 to 99%, which was very good. We have enough aqueous phase within the gel. We can control this also by changing glutaraldehyde relative amount very easily. Loading is excellent because when you start with the dry cross-linked gelatin macrospheres, you bring them together with phage nanoemulsions that we prepare with a certain volume. They just suck up all the nanoemulsion or the aqueous phase, and loading is 100%. This is rather very unique in this kind of gels. Usually very low loading efficiencies are achieved in many of the carriers. What we do here is we look first T4 phase release from gelatin macrospheres. In 24 hours, as you see, depending on the glutaraldehyde we use, 3 different relative amounts, but all of them release in 24 hours. There's a difference of release behavior, but not that significant. This was actually we were aiming, because severe infections, you need high loading at the initial period of treatment, high loading, high release of T4 phages. What happens if they find any bacterial, their targets, anyway, number will increase very significantly in few hours. So we want them to have a release in the first 24 hours. In this case, we are looking BFGF release from gelatin macrospheres. It's a well-known growth factor to increase the angiogenesis, or therefore regeneration of the tissues. It has been already used in many, there are even clinical application of this, but it's controlled release. But the releases should be sustained. As you see when we use basic gelatin, similar to phage, it releases very fast. This is not good. So we decided to use acidic gelatin. EIP is 5, means that at physiological pH 7.4, it will be negatively charged. BFGF is positively charged because its isoelectric point is around 9.6. So they interacted very strongly. Not all of them. Some of them in the pores, they release fast, but then you reach a plateau. It means that they're going to stay in the matrix. But this is in vitro study. But when you use in vivo, gelatin phase will be degraded and they will be released during the period of regeneration. She was able to isolate mesenchymal stem cells from adipose tissue. It's a standard procedure. And 2D culture of them to increase the number to reach certain concentration that we can use in further studies. And then she was able to prepare mesenchymal cell aggregates with or without gelatin. Here you see, you bring them together, suspension of mesenchymal cells and suspension of gelatin microsphere, and you put in the culture wells, round bottom, and they go and accumulate there and form spherical shape microspheres. As you see here, we did both 2D and 3D culturing. You see the results of 3D culturing, A, B, C. We followed them about 14 days. At the beginning, you don't see too many cells around, but when you go further in time, there will be dense layers because they are connecting each other and forming 3D structures like spheroids. These are not spheroids, actually. They have gelatin inside. Gelatin is good because it's like a connective tissue in vivo. If you don't use them, look at the bottom right, almost most of the cells start to die because there's no gelatin in it. I will show only two pictures here. One is about living cells, number of living cells. As you see in the bottom, this line is 3D structure without gelatin. And the one with open rectangulars is 3D with 3D mesenchymal cells with gelatin. There is a huge difference. The number of the cells increasing in 7 days very significantly. This is the effect because they contact with each other and they like each other and form a 3D structures already. This one is 2D. There is no, these are flat tissue culture dishes, and there is no diffusion limitation, though, so it is accepted that their number will increase in time. And I reduced because normally it should be 15 minutes talk. And at the last moment, we find out that it will be 10 minutes. So I took only one metabolic activity graph. Let me try to explain. We look glucose in time. We're taking samples from the culture dishes. We look glucose consumption and lactic acid production. Lactic acid production to glucose ratio shows the metabolic activity. If it is low, activity, it means that activity is high. So here, as you see, in first 6 days, activity in 3D agricultures with gelatin macrospheres were quite high. The activity was high, even higher than 2D cultures. There's no diffusion limitation there. Cells are sitting on as monolayers. But in time, as expected in 7 days, there will be some differences. 2D is better. But I think you have so many cells here, it's much more better than normal 3D spheroid structures of any kind of cell because of the gelatin. So I think I should stop here. Teşekkürler in Turkish means thank you very much. Hope to see you again in another meeting. Thank you.
Thank you very much, Dr. Piskin. So we're going to go to next speaker, Madharima Deb from India Institute of Technology, Bombay. The presentation title is Sensing of Lead Using Graphene-Based Chemi Resistive Sensor.
Am I audible? Ma'am, do you have my video?
Ching Chen,
Yeah, I
are you
have
going
the
to play a
video.
video?
Yeah,
Okay.
we want to play the video.
This is Madhurima Deb and I'm pursuing 4th year of my PhD under Professor Shobha Shukla in the Metallurgical Engineering and Material Science Department, IIT Bombay, India. Today I would like to present my work on sensing of lead using graphene-based chemi-resistive sensor. Heavy metals such as arsenic, lead, cadmium, mercury has a tendency to accumulate in our body by binding with proteins and cause many adverse effects such as neurological and gastrointestinal diseases. Studies have shown that many of the major rivers in India contain heavy metals such as lead, cadmium, nickel, and chromium greater than the permissible limit. The preliminary sources of these heavy metals are industrial effluents from tannery, battery and electronics industries, household pipes, fossil fuel combustion, as well as landfill leachates. So it is the call for the day to develop efficient sensors for monitoring the heavy metals in water. Commercial detection techniques come with some limitations. For example, ICP-MS or AAS are highly accurate, but the instruments are bulky and expensive. Also, it involves expert operators, complex sample preparation, as well as high power consumption. Not only that, real time or on field detection with this kind of techniques is not very feasible. Over the past two decades, many lab-based techniques have evolved, such as SIRS-based sensing, fluorescence-based sensing, electrochemical sensing, and FET-based sensing. Many 2D nanomaterials have shown desirable properties to be utilized in developing sensors. Graphene or graphene equivalents are one of them. We have tried to develop a two-probe chemi-resistive sensing technique for lead detection in water. The setup is very simple as shown. According to the best of our knowledge, this is the first time graphene-based chemi-resistive sensing of lead is reported. Now, moving on to the details of our study. For the device making, we have started with graphene oxide film on glass cover slip. We have reduced graphene oxide with hydrazine monohydrate and then dried the film at room temperature, followed by thermal annealing and then subsequent cooling. After the cooling is done, then beta cyclodextrin is added or drop cast on the film and then it is again dried to 100 degrees Celsius. After subsequent cooling, electrode making is done and then the samples are stored for 12 hours before measurement. These are the experimental steps for the study. For the composition optimization, we have checked with different GO beta cyclodextrin ratio and we have found that the ratio 100:1 was the best one in terms of the lowest base resistivity and the most stable one because of the least standard deviation. So we moved forward with that ratio only. When we were analyzing the morphology by scanning electron microscopy, we found that the red circles are indicating high concentration of lead, which was quite clear on top of the surface. And when we zoomed in a little bit, the difference in lead concentration in area A and area B, that means defined by 1 and 2, are also quite understandable. Moving on to the mechanism of lead trapping by beta cyclodextrin. As we have already known by looking at many previous studies, the secondary hydroxyl groups are responsible for the divalent cation trapping by beta cyclodextrin, and the deprotonation of secondary hydroxyl group takes place mostly in the alkaline condition, and that is the main step for the capturing of lead ions. And the internal cavity of the beta cyclodextrin molecule plays a huge role in this. The truncated cone formed by the 7 glucopyranose units is shown here. In the second image, 1 glucopyranose unit of the beta cyclodextrin molecule is shown. When the lead comes into the picture, then the one lead ion is interacting like this with 2 adjacent glucopyranose units. Did the systematic study of response by RGO-BCD towards different concentrations of lead. This is how the response looks like. That is, when we are increasing the concentration of lead nitrate solution, the response was increasing. But when we were comparing the response towards lead and the response towards other heavy metals such as cobalt, chromium, and cadmium, we saw that the response towards lead was quite better as compared to the others, even when we move towards higher concentration like 500 ppm, the response towards lead was much better than that of cadmium. But we also saw we have done comparative study between RGO and beta-cyclodextrin functionalized RGO towards lead sensing. We have seen that functionalized RGO is definitely much better in terms of sensitivity as well as selectivity, and RGO was not very sensitive and selective towards lead. And this is the calibration curve for RGO BCT 100:1 towards lead.
Chi-Chen, I think we're frozen.
This is the prototype of the packaged device that we have tried to develop. The first image shows the 3D printed housing, which has 3 inlets. One is for the analyte addition and the 2 others are for the probe insertion. The housing is movable on the sensor substrate lengthwise for multiple measurements on a single film. So this was a very short representation of the work that we have been doing for Chemi resistive sensing of lead using graphene-based material. I would like to thank Professor Shobha Shukla and Professor Sumit Saxena for their constant guidance and support, and definitely all the members of NemoLab and Victory IIT Bombay. For funding, I would like to thank DST India, and for the characterization, I would like to thank SAF and IRCC IIT Bombay. Last but not the least, I would like to specially thank all the organizers of AFM UCLA 2021 for organizing this amazing event and giving me this opportunity to present my work in front of all the great minds working in this field. Thank you so much.
Thank you. We actually have time for a question. If there's any, you can either raise your hand or type in the chat. Okay. If not, we'll go to our next speaker, Si-Young Kim. And the presentation title is a vibration-assisted nanosyringe structure using carbon nanotube.
Can I share my screen?
Yeah, it's all good. Go ahead. Si-Young, we cannot hear you. We can see the slides, but we cannot hear the voice.
No.
We see the title page, but we still don't have the audio. Chi-Chen, maybe you can help. I see that.
Yeah, you want me to share the video you recorded?
Yes.
Okay. If you want to share it yourself, probably when you do the share screen, you need to enable the sound, which is at the bottom of the screen.
Okay, thank you.
Okay.
Yeah, I see. Can see. Hi, I'm Seon Kim from Yonsei University. Hi, I'm Seon Kim. Now?
Yes. Can you play a little bit louder?
Okay. Kim from now? Is it okay?
Yes. Go
Okay,
ahead.
thank you. Yonsei University. Hi, I'm Seon Kim from Yonsei University. I'm going to talking about vibration-assisted nanosyringe structure using carbon nanotube. Nanoneedle has a great advantage of avoiding skin irritation caused by repeated use of a syringe. However, nanoneedle has some problems. Because of their nanoscale length, nanoneedle requires high aspect ratio. However, it is hard to fabricate nanoneedle with high aspect ratio, and even when success to fabricate the nanoneedle with high aspect ratio, because of their small diameter, they are brittle. Therefore, it is hard to penetrate nanoneedle into skin tissue. To overcome this problem, one of the recent studies utilized the Elastomer Patch. The approach prevents the needle breaking during the penetration. However, the system needs to attach the additional elastomer patch on nanoneedle surface, so it is hard to say that the approach fundamentally solves the penetration problem. Another research utilized electroporation to improve penetration. The approach efficiently decreases the puncture force when penetrating the needle, but it severely damages skin tissue. So we applied triple-walled carbon nanotubes as a nanosyringe model. Carbon nanotube has a needle-like geometry with a high aspect ratio and good mechanical properties, such as a high thermal and electrical conductivity, high tensile strength, etc. These properties can prevent the nanoneedle breaking during the penetration. In addition, large surface area of carbon nanotube enables various functionalization to either covalent attachment or non-covalent absorption with drug molecules. This allows great potential to carbon nanotube as a nanosyringe to deliver drug molecules. It has been reported that the triple-wall carbon nanotube structures exhibit oscillatory behavior depending on the lattice incoherence of their inner and outer wall. The authors expect that the oscillation behavior of triple-wall carbon nanotube can reduce the interaction between skin tissue and carbon nanotube molecule, then finally reduce the penetration force. To imitate skin tissue, we adopted the PPC phospholipid bilayer membrane, which has both hydrophilic head group and hydrophobic tail group. Prior to penetrate carbon nanotube into phospholipid bilayer, we tried to stabilize the structure of the PPC bilayer. Therefore, we constrained dihedral around atom phosphorus to prevent the spread of two acyl chain. We also constrain position of the atom to prevent the spread of two upper and lower layers. We conduct a simulation while reducing constant energies, and we confirm that the potential energy is stable at each equilibration phase, and the position of the PPC upper head group and lower head group is constant during the equilibration. After the structural stabilization, we conducted validation of the PPC phospholipid bilayer. First, we compare the trim order parameter of the membrane. The parameter reflects the phase of the membrane. When deuterium order parameter value is close to 0.5, lipid bilayer act like perfect crystal. When order parameter value is close to 0, lipid bilayer act like liquid. Before we estimate the area per lipid, considering the hydration effect, we fill water molecules in a ratio of 30.4 compared to the number of lipid molecules. Then we estimated area per lipid, which reflects the quality of force field. Estimated area per lipid shows that the value is close to 64, which is the experimental value. Prior to penetrating triple-walled carbon nanotubes into phospholipid bilayer, we inserted single-walled carbon nanotubes to obtain the resistance force without vibration. Here is the method of carbon nanotube penetration. We used tiered molecular dynamics to estimate the resistance force during the penetration. We tethered the virtual spring on the center of the mass of carbon nanotube. Spring moves in constant velocity, and the pulling force is applied on the atoms of carbon nanotubes. Pulling force is calculated by multiplying the distance between spring and center of mass of the carbon nanotube and the spring constant K. Initially, the carbon nanotube was positioned at the distance of 3 Armstrong from the water layer. The pulling force was increased until the carbon nanotube reached the water surface. This is because the interaction between upper water layer and carbon nanotube is dominant in the space. After carbon nanotube punctured the water layer, the pulling force reduced until the carbon nanotube reached the hydrophilic head group of the phospholipid bilayer. When the carbon nanotube was pulled to traverse the hydrophilic head group of the bilayer, the required force for pulling became higher because carbon nanotube prevents entering the hydrophilic layer. After this phase, as the number of phospholipid around the carbon nanotube surface increases, the interaction between phospholipid tail and carbon nanotube increases and becomes dominant. Then, when the carbon nanotube located at the center of the DPPC bilayer, the resistance force reached the maximum value. You can see the distance at the peak point of the maximum force is delayed compared to the distance at the peak point of the interaction energy. This is because the pulling force is estimated from the virtual spring. The interaction is maximum at the distance of 57 Armstrong, but pulling force is estimated by the distance between the spring and the center of mass position of carbon nanotube, so the current carbon nanotube position didn't reflect the maximum interaction energy. Finally, after the carbon nanotube passed the center of lipid membrane, the interaction with phospholipid tail group decreased, so the resistance force continuously reduced. As we confirm the maximum resistance force point, our future work is penetrating triple-walled carbon nanotube into bilayer. Prior to the penetration, we plan to design triple-walled carbon nanotube which has sustainable oscillation. Then we will optimize inserting velocity and oscillation to reduce penetration force. Here is the conclusion. We stabilized the PPC phospholipid bilayer and estimated the resistance force and interaction energy during the carbon nanotube penetration into the PPC phospholipid bilayers. Our future research plan is penetrating triple wall carbon nanotubes into the PPC phospholipid bilayer to reduce the penetration force. Thank you for listening.
Thank you. That's very impressive. If no question, we'll move on to the next presentation. Thank you. Our next speaker is Justina Warner from Poznan University of Technology, Poland. Do we have the speaker here, Ching Ching, or we can play the video?
Sure, I will play the video.
Okay, thank you.
Hello everyone, my name is Justina Warner. Currently I am an assistant professor in the Faculty of Chemical Technology of the Poznan University of Technology in Poland. I would like to present the result of a recent study carried out by our team. Application of new thin film solid phase microextraction coating materials based on Dipiotectic solvents for pre-concentration of trace amount of organic contaminants in environmental sample analysis. During the presentation, I will introduce to solid phase microextraction and coating supports, geometries, and coating materials in SPME. Then I would talk about Dipiotectic solvents and their possible use in SPME technique. The solid phase microextraction was developed in 1990 by Professor Janusz Pawlisyn. The basic device for the SPME technique is made of the quartz fiber coated with a thin layer of the extraction medium fixed in the needle. The process of extracting analytes performed by immersion of the extraction fiber in the sample, or analytes are taken from the headspace over the sample. In order to improve the extraction efficiency, new coating supports and geometries, new coating materials are introduced to SPME. New coating supports and geometries in SPME can be divided into two groups. Technique with diffusion mediated by stirring and by flow through. And from the point of view of the study that we conduct in our laboratory, thin film microextraction is important, so I will focus on this kind of coating support for SPME during my presentation. The main difference between thin film microextraction and traditional SPME is that it uses a larger volume of sorbent, which a more developed surface area, which allows a very high sensitivity to be achieved. The first device for thin film microextraction was used in 2003, and since then many modifications have been made, both in the shape of the thin film supports and the materials from which the supports are made. Glass wool mesh or carbon mesh supports were introduced in a few years ago, but we proposed to use the stainless steel mesh as supports. Obtaining a thin layer of coating material in the thin film solid phase microextraction technique is possible using several methods. The most common form of making the thin film layer is deep coating, in which a support is immersed several times in the mixture containing the coating material that is dissolved or dispersed in the solvent or glue. Hot dip coating is one of the most efficient methods for producing coatings with a smooth surface a few micrometers thick. From the point of view of the efficiency of extraction analyzed with different polarities, the type of coating material applied to the support is also important. Commercial and other coating materials for SPME have been known from years. In my presentation, I would like to show the possibilities of using dipiotectic solvents as coating materials whose polarity can be designed before synthesis. Currently, I have found only 5 published studies that use dipiotectic solvents as a coating material in various SPME geometries. However, I believe that these compounds, due to their properties, have great potential as coating materials in SPME technique. Dipiotectic solvents are eutectic mixture of hydrogen bond donor and hydrogen bond acceptor with a low freezing point below 100 Celsius degrees. Dipiotectic solvents has similar properties to ionic liquids, but they are easier to synthesis with no purification and less toxic. As can be seen in the eutectic point diagram, reaching the eutectic point means obtaining a mixture with a much lower melting point compared to the melting points of its components. This allows obtaining dipiotectic solvents that exist as solid at room temperature. The main scope of our research was the preparation of new coating materials based on dipiotectic solvents and their application for the thin film solid phase microextraction technique to isolate and pre-concentrate trace amounts of organic contaminants such as parabens, aldehydes, or pesticide, followed by their chromatographic determination. We have synthesized nearly 70 dipiotectic solvents of different polarities, initially analyzing their physicochemical properties such as solubility in water and organic solvents, solid state at room temperature, and mechanical stability on a support, which qualify them to be used as coating materials in thin film solid phase microextraction technique. During this presentation, I would like to discuss 3 deep eutectic solvents that we have successfully used as extraction media. The compound marked as DES1 was obtained by the synthesis involving the use the docosahexaenol and 3-hexyl tetradecyl phosphonium chloride, and its structure was confirmed by infrared spectra. In addition, the obtained structure were analyzed using the scanning electron microscope and energy dispersive X-ray spectrometry, which showed the surface and confirmed the percentage composition of the elements of the obtained coating material. A similar set of analysis was performed for the compounds DS2 and DS3. The first stage of the analytical procedure relied on the preparation of thin film of dipiotectic solvent-based coating material on surface of the stainless steel mesh. The thin film coating material was dipped in 200 milliliters of sample. Then the solution was shaken to absorb the analytes to the coating material. Next, the support was immersed in the small volume of organic solvent and shaken to dissolve the analytes, which were determined using the liquid chromatograph. Then the conditions for proposed method.
Thank you, Chin. Our next speaker is Nasruddin from Palembang Institute for Industrial Research and Standardization, Indonesia.
Oh, okay. Thank you. I will direct presentation. Share screen, sir. Miss.
Yes, please.
Okay. Okay.
Yeah, good.
Yeah. Okay. Thank you. Sorry. Okay. Thank you for the time. Good afternoon, all. Let me introduce myself. I'm Nasruddin from Palembang Institute for Industrial Research and Standardization, Ministry of Industry, Indonesia. I'd like to present my paper entitled Effect of Composite filler on mechanical properties and material homogeneity in solid tire vulcanization for trolley. Author Nasruddin and Poppy Marlina. Introduction. Airport trolleys in the past, present, and future are still equipment to support passenger activities at the airport. This trolley, solid tire, are one of tire that is widely used by trolleys at various airports. Trolley solid tire have disadvantage because their surface is prone to abrasion. When the trolley is used to move goods, there is a noise that makes the air uncomfortable to hear. Noise is caused by tires that are used and increase in elastic. This noise is caused by the tire become stiff due to aging during the service life. Hardness during aging can increase to 15 sur A. The type material, the ratio of material, and the manufacturing process of solid tire affect the mechanical properties of solid tire, such as density, hardness, and abrasion resistance. The use of natural rubber with elastic properties for solid tire will produce solid tire that are superior to solid tire made from synthetic rubber or solid tire made from natural rubber. and synthetic rubber. Natural rubber is amorphous when it will crystallize and come in from mechanical properties such as their resistance, abrasion, abrasion resistance, and tensile strength. Responding to existing, the study used natural rubber with composite filler of calcium carbonate and zeocell. Zeocell composite white calcium carbonate and the optimal ratio will improve the mechanical properties of solid tire, where each filler composite is complementary to provide superior properties. Table 1 trolley solid tire formula. The table 1, these are the four solid tire formula. Effort distance by the ratio of calcium carbonate. For other material, this ratio condition. Solid tire malnutrition process. This material rubber and determine material and additive. This rubber compounding, pulverization process and example trolley solid tire. Result and discussion. Pick 1.1.a, the effect of calcium carbonate ratio of specific gravity on the pulverization of solid tire. The result of the specific gravity test figure 1.a show that for every increase in the calcium carbonate ratio, table 1, there is an increase in the specific gravity value before and after aging. The difference in the increase in the specific gravity after aging is caused by the evaporation of the molecule of the material with a low boiling point during the aging process. 24 hours aging at 17 degrees Celsius. The evaporation of the material with low boiling point during aging not only affect the specific gravity value, but also affect the moment of the bond between the molecules that from the rubber vulcanization. Pick 1.b, the effect of calcium carbonate ratio harness on the vulcanization of solid tire, trolley solid tire. The test results show that when calcium carbonate in ratio increase, the hardness value increase. The was on increase, the hardness value at 75 for calcium carbonate ratio before aging 67 short A and after aging 60x short A. Fix 1.b. The solid tire hardness test result from the airport trolley are the same as the solid tire hardness test result for formula L03 before aging 65 short A. The hardness of the rubber portion is formula by the polyisoprene aldehyde group, while the aldehyde group which is solidified by the additive of filler. Pick 1.c, the effect of calcium carbonate ratio on abrasion the vulcanization of solid trolley tire. The result of testing the formula L01 white ratio of 60 pHr calcium carbonate before aging experience and abrasion of 4.5 millimeter cubic after aging 5.03 millimeter cubic. The use of calcium carbonate with ratio of 60 pHr with experience lower abrasion the other formulas. Silicon dioxide together with calcium carbonate in natural rubber vulcanized composite to improve the mechanical properties and resistance of solid tire to abrasion. In addition, silicon dioxide has better interfacial bonding on the rubber vulcanization matrix. The Pick 1 FTIR spectrum in the range for abrasion 750 centimeter -1. This sample L01 and L02, L03, L04. This table functional group and frequency based on wave number. The FTIR spectrum that in fix 2 show that there are fixed that explain from each sample which has 3 which almost the same fix and almost the same with number position. The FTIR that in fix 2 show that the typical absorption band of natural rubber vulcanization is seen in the wind with number R of 4,000 centimeter -1 to 750 centimeter -1. The most important natural rubber in this spectrum are the carbon strengthened at 16,663 centimeter -1. The carbon hydrogen band of the methyl group on 1,370 centimeter -1, and the carbon hydrogen band on the unsaturated cheese configuration of X137 centimeter -1. Scanning electric analysis of solid tire. Fix 3 500 times magnification SCM microgram of sample L01, L02, L03, and L04. The scan result in fix 3 show that there is an empty space in the rubber vulcanization matrix. That point might be due to the non-uniform size of the calcium carbonate as usual, and the weak van der Waals process between the aggregate. The van der Waals process and the three-dimensional bond network of the cross-linking reaction strengthen the intermolecular bond of rubber vulcanization. The scan result of sample L01, L02, and L04 show the distribution of with particle. This distribution is indicated as the distribution of calcium carbonate, zeoshell, and titanium oxide. Conclusion: natural rubber reinforced white calcium carbonate and zeoshell can be used as filler for the manufacture of solid tire for trolley used in airport. Mechanical properties study on solid tire vulcanization show that the increase in the calcium carbonate is directly proportional to the increase in the value of specific gravity, hardness, and abrasion before and after aging. In comparison of 7P et al., the hardness value of the trolley solid tire from this study is the same as hardness value of the airport trolley solid tire. The result of the functional group analysis show that the effort from each sample correspond to the position of the wave number of the respective substance used. This SIM result show the presence of air void and the distribution of filler on some part of the sample surface. Thank you for attention.
Thank you very much. So due to time limit, we're not going to have time for question. And keep in mind that everyone can reach the speaker directly through the app. Now, please welcome our next speaker, Sarah Bibi from Hazara University, Mazahar, Pakistan. Dr. Bibi, are you there?
Okay. Thank you.
Thank you.
Thank you. Thank you.
Hello.
Hello.
Hello. Yes, I'm there. Hello.
Are you ready to present?
Can you please run my video?
Chi-Chen, can you do that?
Yeah, I will do that.
Thank you.
Okay. Thank you.
Hello?
Hello.
Is there a problem, Chi-Chen?
Yeah, I don't think I found your video.
You cannot find my video?
Yeah.
Okay,
one-
just a
Well,
minute. Just a minute, please give me a time, please.
Yeah.
Hello, everyone. This is Saira Bibi. I'm going to talk about evaluation of polymeric ionic liquid chitin beads as an innovative adsorbents to trace multi-target analyte from wastewater. This is the outline of my research work. First of all, I will discuss about arsenic risk in Pakistan, and then I will discuss about solutions that could be bioadsorbents, and then I will discuss about chitin-based nanocomposites and polymerized ionic liquid-based adsorbents. Pakistan is one of those countries where most of the groundwater is contaminated with arsenic. Even in Punjab province, 20% population exposed for over 10 milligram per liter in drinking water, and 3% population is exposed to over 50 milligram per liter. And in Sindh, 30%, 38% population is exposed to arsenic via drinking water. So you can see here that how much Pakistani pollution is exposed to the arsenic, and how much is the alarming situation, and pose significant health issues due to the arsenic level. WHO recommended limit for our drinking water is 10 microgram per liter for drinking water, but it is exceedingly high in Pakistani water. Now researchers are thinking about to solve this issue, and we are thinking about the cheaper method which we can use for the removal of arsenic from groundwater, and also from some other industrial water. Now we are thinking about the solution. One of the possible solution could be the use of some cheaper adsorbents. We can prepare some cheaper adsorbent from biopolymer. One of the most abundant biopolymer which is present in Pakistan industry is we can extract from fishing industry, that is chitosan, as fishing is the sunshine industry of Pakistan, which produce tons of waste, head, tails of shrimps, crabs, etc. Annually worldwide production of chitosan is too much high. Now problem is that what to do with the colossal amount of the waste. We can convert this amount of waste into the useful material, that is chitosan. Chitosan is a biopolymer, and it is a polysaccharide, and it can be extracted from shrimp shells, etc. This is the more versatile than cellulose because it due to the presence of amino and hydroxyl group. It is biocompatible, biodegradable, and soluble in aqueous medium, and it has complexing ability. That's why we can use it for the removal of arsenic and for other heavy metal, because it has complexing abilities towards metals, toward toxic dyes, and toward fats and some other anionic compound. So for the technological application, we can be modified this kind of material by using a different type of techniques. We can blend it with different polymers, and we can cross-link it, and we can add some different type of nanofiller. Here we just modified this type of material by using polymerized ionic liquid and by adding different kind of fillers. Polymerized ionic liquid, the application of ionic liquids can be enormously expanded by arranging the organic ions in the form of a polymer architectures. Polymerized ionic liquids, also known as polyionic liquids or polymeric ionic liquids, provide almost all feature of ionic polymers plus a rare versatility in design. So it is well known that many researchers already use polymerized ionic liquid for the capturing of arsenic and other heavy metals. Here we have an idea to combine chitosan and polymerized ionic liquid with the addition of different carbon-based filler. As we all know, there are various kind of carbon-based filler which are used for the removal of different toxic material. For example, single wall, double bond, CNTs, fluorines, graphite, graphene, and graphene oxide, etc. We have selected graphene oxide because graphene oxide have very much better compatibility with chitosan and of course with polymerized ionic liquid, because graphene oxide have oxygen functionalities and our material chitosan have also oxygen functionalities, so it can interact with each other easily. Now the challenging in fabricating polymer-based bio-nanocomposite is control of their synthesis, ensuring the compatibility of different material component and obtaining desirable or unique properties. The foremost motivation of the project is to develop multi-target material by granulation method intended for the purification of Pakistani pollutant water. Different approaches and new procedures were exploited. Consequently, various hybrid novel adsorbents were developed. The resulting materiality was successfully tested on lab scale to remove chemical contamination of various materials like arsenic and copper, etc. And different type of dyes are also tested. Our first step of the project was the synthesis of pyridine-based polymerized ionic liquid. We have used different kind of procedure for the synthesis of pyridine-based polymerized ionic liquid. The three-step synthesis include the direct free radical polymerization, that is the synthesis of homopolymer synthesis, quaternization, and anion exchange reaction. This is the scheme for the synthesis of poly,4-vinyl octyl bromide. This is the here you can see the physical appearance of the material. These are the photographic images which were taken during the synthesis of pyridine-based polymerized ionic liquid. This is the IR spectrum which confirms the presence of, the conversion of monomer to the polymerized ionic liquid. This is the synthesis of chitosan polymerized ionic liquid and chitosan polymerized ionic liquid graphene oxide based beads. We just combine these all ingredients by using simple sonication method, simple blending, no other kind of cross linkers or any other kind of complex reactions are used in these procedures. At the first step, we just synthesize beads by using peristaltic pump. This is the very simple technique. Here you can see dry beads and dry beads without graphene oxide, and these are the beads with graphene oxide. Our basic purpose for the synthesis of this kind of beads was using prilling technique. We want to use prilling technique to industrialize and to commercialize this kind of materials. But in the first step, we have just synthesized these materials by using peristaltic pump. But our basic aim is to convert this technique on the prilling technique and to produce on a larger amount. This is the SCM image of beads. As we have used chitosan and graphene oxide and polymerized ionic liquid, chitosan alone, graphene oxide alone, and polymerized ionic liquid alone have very good good characteristics, good ability towards arsenic capturing and for copper and for other heavy metals and for other organic pollutant. We combine as these materials, so we are expecting that the potential application for this kind of material could be the adsorption for almost all kind of material, because we have graphene oxide. It can capture organic pollutant, inorganic pollutant. We have polymerized ionic liquid, it can capture different heavy metals, and we have also chitosan. It is porous in nature, so it have the ability, well-known ability to absorb toxic pollutants. At the first step, we have checked the removal of arsenic, and we use ICP OES technique. We just dipped different amount of beads into the chitosan solution, into the arsenic solution. The initial arsenic solution was around 10 milligram per liter. Here you can see that after the addition of chitosan blank beads, the remaining concentration was 3.64. It means that our material efficiently absorbed almost around 6 to 7 ppm, 6 to 7 milligram per liter of arsenic from the solution. And chitosan polymerized ionic liquid, after the addition of polymerized ionic liquid into the chitosan, the adsorption capacity of the material was enhanced, and after the addition of GO, the adsorption capacity of the material was further enhanced, but it was not too much enhanced as we are expecting. It might be due to the I don't know why the adsorption capacity of the material was why not too much high, but we can achieve our desired results by altering the procedure, maybe by adding different kind of carbon based material, or maybe we can use different kind of pyridine based polymerized ionic liquid. Here you can see the IR spectrum of the material. In our results, we have noticed that chitosan actually play the important role to capture arsenic and some other heavy metals from the material. We have also tested chitosan GOPs system for the adsorption of copper. Here you can see the results for copper. After the addition of polymerized ionic liquid into chitosan and GO system, the adsorption ability of the material was greatly enhanced. Here you can see the images of beads after copper adsorption. We have also tested some dyes, toxic dyes, that is methylene blue. Here you can see the spectrum that methylene blue was also removed by CS spills. To conclude, the properties and application of the developed material were quite promising. Furthermore, such newly developed material provide new addition in water engineering, chemical synthesis, membrane separation technologies. I am very much thankful to Peridot Park French project, very much thankful to the University Savoie Mont Blanc Chambéry, France, and Pakistan Institute of Engineering and Applied Sciences, Piaz, and Higher Education Commission Pakistan for providing funding for this project. Thank you very much. If you have any question, you can send me an email or you can ask now. Thank you.
Thank you very much. So I don't see our next speaker in the room. Chi-Chen, can you get prepared to play the video? Our next speaker?
I don't have the video for the next talk.
You do. I see in the Dropbox.
Okay.
It's a number 11, high frequency response of biomass derived carbon in aqueous electrochemical capacitor. Number 11 in the Dropbox.
The next talk should be the number 10.
No, after Dr. Bibis is Elżbieta Frakowiak from Poznań University of Technology, Poland. It's labeled 11 on the Dropbox.
Oh, okay.
Hello everyone. My today talk concerns high-frequency response of biomass-derived carbon in aqueous electrochemical capacitor. The work was done in 3 different institutions: Poznań University of Technology, Slovenia, and University of Zaragoza. I want to speak about electrochemical capacitor, but only about properties which are charging, discharging during 1 second. And everyone knows that electrochemical capacitor is a device of high specific power, which is not able to reach in the family of accumulators. Here you see some kind of a very basic formula for energy, power, and capacitance. You see that charging of and discharging of electrical double layer is based on electrostatic attraction of ions in electrode-electrolyte interface. Now, where we are using materials reaching nitrogen functionality, because nitrogen-doped carbons can have high conductivity because of modification of electron density, high capacitance because of redox processes which are observed on the right side, and because of wettability. We are preparing our materials as the following. Adenine was a precursor, and we are using salt templating synthesis, where KCl was playing a role of template, whereas the chloride of zinc was activator. Salt to salt ratio was 1:1, whereas salt to precursor ratio was 10:1. Such kind of mixture was after pyrolyzed in oven at 900 degrees C. And on the right, you see scanning electron microscopy of this material. And the electrode material was composed on activated carbon, Teflon, and carbon black. 1 magnesium sulfate play a role of electrolytic solution. Here you see the transmission electron microscopy images of both carbons, because adenine was our carbon prepared as a new one, and it was compared to YP50F, which is typical industrial carbon produced by Kurari, Japan. So you see that here you have some kind of microporosity quite loose, and this one is more dense. You see graphite layers are quite dense. But here it is very important to see that this material in the lower magnifications has some kind of chain structure, whereas here you see some particles that are disconnected. It will play a role for conductivity, but also for preparation of electrode as a flexible plate. Here on this slide, you see some BT specific surface area for both material. It is a powder, and here electrode. Electrode is, of course, you are losing some porosity because of Teflon and some conducting additive. For YP also, electrode powder and electrode material, both. BET specific surface area slightly is diminishing, microporosity as well. But what is the difference, main one between two materials is that this one has mesoporosity, especially from 2 to 4 nanometers in this region. And this one has no mesoporosity at all, 0.1 only. So it is the biggest difference between these two materials. For particle size distribution, you see that YP, this Japanese material, has very homogeneous one size of particles, around 10 micrometer, whereas adenine, KZ material, has very broad particle size distribution, but it improves some interparticle contact. Here you see some composition of this material by XPS and by elemental analysis. In this material, nitrogen by XPS is 4.6%, whereas by elemental analysis is double more, 9.4, because it is some kind of quaternary nitrogen which is present in the matrix. You see here that pyrolic nitrogen and pyridinic is around 28, 16%, whereas quaternary is very high amount, 54%. So half of nitrogen in our material originates from quaternary nitrogen. Nitrogen is quaternary here and improves very much conductivity of our material. Here you see electrochemistry, cyclic voltammetry with different type of scan rate from 1 to 50 millivolt per second. You see perfect square-shaped voltammogram, very nice. Here you see some separation of negative electrode and positive electrode, also very nice square-shaped voltammogram. Whereas going from 1.5 volt, you see some kind of pseudo-capacitive properties which is visible here, some additional growth. And here, separately negative and positive, you see also some kind of irregular voltammogram. The most important slide is presented here, where you see capacitance versus frequency. So at 1.5 volts, our capacitance with adenine keeps very nicely capacitance until 1.7 farad per gram. So it is very nice charge propagation. Whereas for YP, you see that capacitance is already lost at 1 Hertz, has only 42. So definitively higher drop of capacitance. If you will compare long-term cyclability, so for YP 50F carbons, you see very nice cyclability, the same as for adenine. So both of them, they have very good long-term stability. And before aging and after aging, you see what is changing some physicochemical properties. So specific surface area slightly dropping, especially for positive electrode. For negative, this drop is lower. And you see here that positive electrode is losing slightly properties as well. We also compare some kind of density of both materials and conductivity. So conductivity measured by the right electrodes is shown here scheme. You see here 8 millisiemens per centimeter and YP 44.3. So definitely better conductivity for our new materials. However, density, you see that there is double smaller. The same material, but by electrochemical impedance spectroscopy measuring in Swedge log, you see that for ESA, equivalent series resistance is 0.6, 0.6, the same for both materials. But here you see around 0.9 ohm for equivalent distributed resistance, where here you have 3. So again, adenine is better for this parameter. For low frequency, it means 1 millihertz, which reflects very low regime, 0.1 ampere per gram. You see the parameter, they are the following. Gravimetric capacitance is better for adenine, but volumetric is definitively better for YP because it is more dense. But if you want to use our material for high frequency, it means for mobile application, it means for electromobility, where you are using 10 ampere per gram. Both materials are comparable concerning volumetric capacitance, and even gravimetric capacitance is definitively better for adenine. So it is playing perfect role for both applications, finally, stationary and electromobility. Unfortunately, self-discharge for adenine is bigger because we are losing from 1.5 volt until 0.9 volt. And here for YP, because there is lack of self-functionality, self-discharge is lower, it drops to 1.2 volts. And of course, leakage current is also bigger for adenine, so there is some kind of disadvantage. As a conclusion, our new material from adenine shows only very small drop of capacitance going from 1 millihertz to 1 hertz, owing to special morphology, which was shown by transcranial microscopy. This gravimetric capacitance was very high, equal to 140 farad per gram, because of good porosity, ultra, but also small mesoporous and nitrogen functionality. High conductivity was reached because of nitrogen. Optimal amount, 9.4%, 8%, and its modification of electronic structure. Lifespan was good for both materials. They are going very nicely during floating and during cycling. So this work was done in the cooperation between 3 institutions: University of Saragossa, National Institute of Chemistry, Slovenia, and our university, Poznan University of Technology. Thank you very much for your attention.
Thank you. Our next speaker is Yahya Bahra from University Hansen II of Casablanca, Morocco. Chichen, I think you can play the video.
I don't think the video is uploaded in the Dropbox.
No?
No,
What about the 12?
the 12 is the next one.
I see. Yeah, you can go ahead to play the next one. I don't
Okay.
think the other speaker, and we're running behind.
Okay, that's a good idea.
Thank you.
Hello everyone, hello their organizer, hello scientific community. So I'm so happy to contribute in this beautiful event that in University of California, Los Angeles from Morocco, as we know that the COVID-19 doesn't allow us to move to USA to assist to this beautiful event, but we're going to contribute and online mode is good also. So first of all, I would like to thank American Association for Advance in Functional Materials for organizing this beautiful events. So today we're going to begin our work named Synthesize and Characterization of Hydroxyapatite Reinforced Ketone Composite Hydrogel for Bone Tissue Regeneration, done in University of Hassan de Casablanca, Morocco, in Biomolecules and Organic Synthesize Laboratory. So the plan of our work is an introduction, then an experimental details and results and discussion and conclusion of our work. So the normal human body has about 200 bones which are needed for a variety of functions within the body. There are many functions which bones are in the body. Function 1 is support. So the bone is provided support structure more on the hardest and the most rigid structure in our body. Bones are strong but light, which give the body support and shape without weighing it down. So function 2, protection. So the nervous system is the most important in our body. So because the nervous system controls the rest of our body and is very fragile. So the bones can protect this system, such as skull and backbone. So function 3 is movement. So the skeletal system also closely interacts with the muscle system in our body. So muscles are necessary to attach to in order to contract and cause motion. So the last one is blood cell production. So the bone are also important as a center of the production of blood cells. The inside of bone is filled with a gel-like materials called the bone marrow, which is where red blood cells are made. So the bone structures consist of compact bone and spongy bone, where inside contain a bone marrow. So the compact bone is very dense in the outside. Inside is the spongy bone, which is high porosity. So the composition of bone are inorganic and collagen fiber. So the mass of inorganic is calcium phosphate that contain approximately 60 to 70% as bone mineral. So the bone mineral is hydroxyapatite, which is one of calcium phosphate phase. So from my work, chicken eggshell has been used in the hydroxyapatite synthesis as the calcium source. So the chicken eggshell consists of two main parts. The inside of shell, so the inside of is shell membrane, which is contain collagen and other. So this part of shell will be removed before use. So the outside part of shell is which are the mass of calcium compound is contained approximately 95%. So the calcium compound is calcium carbonate phase about 94%. So the chicken eggshell is full of calcium and can be used for hydroxyapatite synthesizing. So hydroxyapatite is the inorganic mineral found in bone and teeth. So it has a high biocompatibility and bioactive. It can use in several applications such alveolar ridge augmentation, maxillofacial reconstruction, orbital implants, pin fusion, repair of bone defects. So the modes of application of hydroxyapatite relate to the bioactive properties of it. So, according to previous research, hydroxyapatite can be synthesized by several methods. For example, solid state methods is very simple methods, that is the reaction of calcium group powder with phosphate group powder in the furnace or ball mining machine. So this method can produce the hydroxyapatite powder easily, but the particle will be large and lack of purity. So the sol gel method and the sol gel method and the sol gel is the mass method to synthesize hydroxyapatite. So this method produces dense hydroxyapatite and so dense hydroxyapatite in small particles. But disadvantages of this method are the high cost of precursor and low throughput. And the last interesting, similar to the sol gel method, but this method is unnecessary gel method, but this method is unnecessary the formation of gel. So the time of synthesis may be shorter, and the hydroxyapatite powder are formed into solid and precipitate in the solution. In addition, the condition of synthesizing can be easily to control and byproducts are easy to remove. So in our work, we're going to use the wet chemical method. So this is a figure explain how we synthesize a biocomposite from hydroxyapatite and chitosan film. So the hydroxyapatite was extracted from eggshell waste, and chitosan was extracted from crustacean, and the DDA of the chitosan was about 90%. So this is a schematic diagram of the synthesized hydroxyapatite from eggshell waste and chitosan composites. So hydroxyapatite and chitosan composite was characterized using FTER and scanning electron microscopy and also XRD. So this is a Fourier transform infrared spectra of hydroxyapatite and ketone composites. So as we see in the FTER here in the purple is the pure hydroxyapatite and a different amount of hydroxyapatite and ketone film. So the pure hydroxyapatite shows a significant peak in the region of 1000. It relates to phosphate group. So here we see that the intensity and sharp of the peaks increase when we increase the amount of hydroxyapatite. So that is confirms that the hydroxyapatite was successfully added to the ketone. So this peak of this band, significant bands, is related to amide and methylene of the ketone. And the last one is pure ketone. So this is the thermogravimetric analysis and DHC of hydroxyapatite and ketone biocomposite of hydroxyapatite and ketone film. So as we see here, a significant weight loss in the region of 100 or 120 is related to the degradation, or is not degradation, as is the deposit of water, and here a significant weight loss is mean the degradation of the polymers. So the polymer was degraded in the region, and this was confirmed by the DAC. So here we see the melting point of the polymer, and at this temperature we see the degradation of the polymers. So the degradation of all the samples, which mean 10%, 20%, and 30% of hydroxyapatite and ketone. So the hydroxyapatite, we can conclude that reinforce the thermal stability of the polymers. So let's go into talk about the morphological structure of the surface. So to confirm this analysis, we use the scanning electron microscopy of hydroxyapatite and ketone film. This image A as the ketone
Okay, thank you, Chichen. Our next speaker is Sandra Scagulucci from IPM Brazil. Hi, Sandra. The stage is yours. You're muted.
Okay. Oh, okay.
All right. Yes.
Okay. Can you put in my video, please?
Oh, sure. I can share your video.
I can't share my video. Yes, thank you.
Hello, everybody. I will talk about the study of mechanical and chemical properties stability of inner tubes exposed to gamma radiation. My name is Sandra, I am from Spain, and this is my co-workers that collaborates with me about this work. Nowadays, car tires are not provided with inner air or tubeless, point toward a technical evaluation. Neither trucks tires even use at present inner tires. This is the photo if inner tires for a trunk, almost fully by a synthetic material. Currently, tires are constituted by various components besides synthetic rubber being a product that aims to a long time of utility life, considering that they are designed and manufactured to last under extreme physical, chemical, and thermal conditions. If it presents complex structure with the purpose to assign requiring characteristics to its performance and safety built to be indestructible. This is the photo that the tires, the components of the tires. Treat, sidewall, belt plus, inner liner, bread sealer, radial cord in the beds. These studies is focused by inner liner. Conventional tires that will still employ air chamber are inside to be crushed and consequently recycled. There are about 450 tires plants all over the world. Tire sales worldwide a drop currently due to the pandemic, but the numbers were up since 2018, where they accumulate 59.4 units. A specific inner line, a specific rubber compound, is used as an air seal inside the tire. The inner liner has a no-cord reinforce and is similar to an inner tube. Our chamber inside the tire is composed by butyl rubber, a synthetic material having a major characteristics, elasticity, and capacity to impede air leakage. The air chamber is located inside the tire that does not have any extra sealing in the well to stand compressed air. The inner tube, located the inner tube is here in this place. The valve that allows the filling is connected directly to the chamber, increasing risk and injuries caused by negligent maintenance. However, the recycling of solid residues that to a right energetic cost and during the process was just car tires. This photo shows the tire chambers for trucker, air chamber for motorcycle, and air chamber for bike. For this study purpose, there were removed samples for production tire chambers for trucks given by manufacturers of these materials whose name is not authorized to divulge. Tire chambers received were used without any previous treatment and were characterized regarding their physical, chemical, and mechanical properties. Samples were subjected to gamma radiation 5, 10, 50, 20, 25, and 30 kilograms dose. The doses are subjected to controlled degradation for the material of the material. We use ionized radiation for cobalt source and oxygen atmosphere. For characterization, we use the CHN elementar analysis, tensile and elongation break, thermal aging, and hardness. We use the STM norms. For elementary doors, we notice the results of elementary nodes. We notice that for carbon and hydrogen, the values is very, very similar. Only the nitrogen, we notice some difference in values. Tensile in the elongation break, we notice the sample not irradiated is higher than the other samples. We notice it's causes some degradation material. For elongation at break, we notice the sample not irradiation is less than the samples irradiation. It's since the break transition. Thermal aging, this test is doing in the oven air for 72 hours. And after and before, these results shows after and before aging. After aging is the before aging is the black color, and the after aging is red color. We notice the similar values for all the samples irradiated. For the sample not irradiation, we notice a little decrease in values for sample aging. It denotes some degradation of the sample. This is the first elongation break. The samples are after aging. We notice a high values after aging. It denotes a break of season because a little molecules has a more elongation. For the results of hardness, we notice, for example, no irradiation is higher than the sample irradiated. But the values for samples irradiation is very, very similar. We notice a softness materials after irradiation. So my conclusion is elementary analysis did not reveal significant changes in carbon and hydrogen levels present in all irradiated and irradiated sample, indicates that even after shearing, the amount of atoms from the polymeric chain was preserved and conserved. Tensile and elongation break mechanical tests showed for irradiated sample values decreasing in function of rise in dose, suggesting the occurrence of chain season because smaller chains present smaller elongation and suffer rupture easily. Hardness result that indicates material rigidity presented low values after irradiation. This is probably caused by degradation mechanism that leads to a depolymerization, for example. Weakening of a elastomeric matrix caused by chain season and or a raised crosslinking. So, analysis shows that it's possible to accomplish controlled degradation of truck tire chambers, considering that in doses higher than 15 kilograms occur chain season. My acknowledges for FAPESP by financial support and IPEM for making the analysis. Thanks for your attention. This is my email for further correspondence. Thank you.
Thank you very much. Thank you. Now we can move on to our next speaker, Yashwacharji Sichang from University of Mauritius. Chi-Chen, can you please play video number 14, design of a lightweight fiberglass stork for fan palm camouflaged cellular tower?
Hello, my presentation focuses on the design of a lightweight stork for a fan palm camouflage tower. This study performed at the University of Mauritius considers the local environmental condition and its impact on such structures being erected in the island. This picture here shows a fully mounted tower perfectly disguised in the form of a natural fan palm. However, this is far from what you would see in practice. I will start by mentioning the drawbacks of the current design of the stalk and how a new shape, inspired from real trees and use of the composite material, can solve the problems encountered. The rationale behind the use of fiberglass will be explained, and the whole methodology for the redesign of the stalk cross-section will be described as the model is eventually tested in extreme wind conditions. The results will be discussed, and the main points will be summarized in the conclusion. This picture here shows a tower in practice. As you can observe, most of the leaves have undergone permanent deformation, and the tower seems to have lost some of its leaves. This makes a very unsightly structure which can easily be differentiated from a tree, failing to accomplish its purpose of being camouflage. The problem actually lies with the stalk. The lack of flexibility of the current stalk makes it prone to crack formation or even breakage under the slightest twisting or bending caused by weather conditions. A 3D model of the current stalk is shown here. It has a top surface which is flat. It has a triangular cross-section at the base, which gradually changes to a rectangular one at the tip. It is made of HMWP polyethylene and has a weight of 20.4 kilograms. The shape and weight of the stalk also plays an important role on the durability of the tower, which is subjected to bending moment due to wind forces acting on the leaves. The proposed design of the stalk will have features of a natural stalk, making it lightweight, flexible, and cyclone resistant. The size of natural stalks gradually decreases from base to tip to reduce the weight and to make it more flexible at the end. Being more flexible not only makes the stalk behave naturally, but also increases its durability as it absorbs a major shock caused by wind gusts. Failure of stalks actually occurs due to bending or torsion. Bending occurs due to the direct action of the wind, while twisting is mainly encountered when there are smaller branches connected to the main one. Studies of composites as a material for tower structures have been very encouraging so far, with both carbon fiber and fiberglass having shown to increase stiffness and flexural strength. Fiberglass is lightweight, has a high flexural modulus. However, it is much less stiff than carbon fiber, which makes it a good choice for the stalk. Epoxy S-glass fiber will be used in this work. Its composition is 65 to 70% glass fiber and 30 to 35% polymer. It has greater strength than HMWP and can be molded in complex shapes. Specific features identified from cross-section of natural stalks have been represented by various parameters, as shown in the figure on the left. Parameters C and D define the width of the cross-section, while parameters A and B are related to the top and bottom of the stalk. The same parameters have been incorporated in the proposed shape, as shown in the figure on the right. There's one additional parameter, which is small t. It has a value of 0.09 meters, and it allows bonding of the leaves to the stalk. This table contains the values for factors A and B for 5 branches from 5 different trees. The branches are of slightly varying length. However, the averages of A and B are extrapolated for a stalk of 1.75 meters using simple proportionality. To determine the optimum values, 5 levels were considered for each parameter, allowing 25 different combinations to be tested. This was done to determine the influence of the various parameters on the structural behavior of the stalk. The different scenarios will be tested under cyclonic wind conditions, with wind of greater intensity than normal winds. Furthermore, a partial factor of 1.6 as used for variable action on steel towers in densely populated regions is applied in the load calculation. A static structural analysis is carried out on this workbench with the base fixed for a length of 300 millimeters. The different weights are the weights of the stalks and the leaves, in addition to the wind pressures. The wind force of the leaf is a main load as it comprises of the frontal, drag, and frictional forces. Two criteria are used for evaluating the stalk. They are displacement and equivalent stress. To ensure that the selected stalk maintains a good flexibility while also being resistant to strong winds, a high value of displacement and low equivalent stress combo will suit the purpose. Therefore, based on the FEA results, the displacement to stress ratios are therefore used to narrow down the best possible choice of stalk. And consequently, the stalk with A equal to 0.02 meters and B equal to 0.07 meters is selected for further analysis. The results of the simulation carried out on the stalk are shown in these figures, with a favorable maximum stress and a deflection of 0.06 meters at the tip. To increase the deflection and reduce the weight of the stalk, material was removed internally, especially in regions where the stress is relatively small. The stalk is made completely hollow by removing different volume of material along the length of the stalk given its tapered nature. Following optimization, the maximum stress was still well below the modulus of rupture, and the displacement increased to 0.08 meters. This makes the stalk flexible and lighter. Furthermore, a flexure of 20 degrees was given to the stalk so that it can have a more natural look, as shown in the 7th figure on the right. This only slightly decreased the displacement to stress ratio. To validate the FEA results, a similar test was carried out on a miniature prototype of the stalk. There was a percentage difference of 0.89% between the values of displacement obtained for the experiment and an equivalent simulation. The stalk is actually more delicate in compression than in tension. The lower part of the stalk is in compression, and the lower value of A, as obtained for the selected model, increases bending and leads to a more flexible structure. In contrast, a high value of B, which represents the depth of the top curvature as used in the proposed model, increases flexibility. To conclude, the nature-inspired shape of the stalk has shown to be very effective in increasing flexibility and durability while also improving the appearance of the structure. Using fiberglass, it was also possible to make the structure hollow throughout, leading to a reduced weight of 16 kilograms, which is 4.4 kilograms less than the weight of the existing stalk. It should be noted that the stalk can have a displacement of more than 7.7 centimeters without breaking, and this could be investigated further. Thank you for your attention.
Thank you. Our last speaker is Benzi Kao from MCA Technologies GmbH, Switzerland. Qingqian, can you please play the video?
Yeah, sure, I will play.
Thank you.
Good morning, everybody. Good morning from Switzerland. Thanks for having me here this afternoon. Looking back, my last visit to the University of California at LA has been over 50 years ago when I was a postdoctoral fellow at the California Institute of Technology investigating mechanisms of enzyme reactions and the nature of inter- and intramolecular hydrogen bondings. It is exciting to note that meanwhile Francis Arnold at Caltech has received Nobel Prize in Chemistry for the directed evolution of enzymes, and cat NMR has become an indispensable scientific and medicinal tool. The summary, the presentation today is about the plastics in general and the smart plastics in particular, their applications and the potential remedies of the environmental concerns of the use of plastics. The knowledge and experience gained from the proposed terminal disposal of the smart plastics by cold incineration could be employed to impart more efficiency to fossil fuels, enabling reduced emissions and less energy losses in their use for the sake of carbon neutrality. This slide shows the picture of Ppm Triazine, the product that we have developed for fire retardancy and processing of plastics, and safe incineration and efficient energy extraction of waste plastics. The synthesis. The slide shows here the solvent-free process for the synthesis of morpholino polypropylenyl morpholenyl triazines. Cyanuric chloride is condensed with morpholine, which is then reacted with piperazine and which is polymerized to chloropolymerizyl morpholenyl triazine and ultimately reacted with morpholine to get chlorine-free Ppm Triazine. The technology is particularly characterized by the fact that for the sake of reducing carbon footprint of the synthesis, no organic solvent is used in any step. Composed of most common harmless elements, the only byproduct of the synthesis is the naturally occurring sodium chloride. Picture shows SEM picture of the particle size and shape of Ppm triazines, which is important for the functionality of this product, consisting of hexagonal shaped individual particles. Incineration and fire resistance of polypropylene composites without and with Ppm triazine technology. Here the tests, we are showing here the limiting oxygen test, index test of flammability. Polypropylene itself burns at 17.2% oxygen content in the air, and it continues burning if not extinguished. Whereas the composites containing Ppm triazine and in combination with various different fire retardants do not burn and form a fire barrier and stop burning after a short time. Mechanism of Ppm triazine technology for fire resistance. We believe that there is formation of ceramic oxynitrides related to graphene as barriers for fire resistance and heat dissipation. Focus in fire retardancy thus far has been on the formation of char that can produce more smoke. In our case, we are aiming at colorless or less char forming residue at the fire point. This is the structure of oxynitrides in combination with inorganic fillers. And this is the structure of oxynitride with phosphorus containing fire retardants. The principle of the synthesis is outlined in this reference. For thermal stability beyond antioxidants in melt processing, in recycling for sustainability. Stability of polypropylene. This slide shows the thermal stability TGA of polypropylene and polypropylene composites 10 and 20 containing Ppm Triazine and ammonium polyphosphate in air versus nitrogen atmosphere. The picture here is the TGA of these various composites showing a difference of 46 degrees Celsius. On the right hand side is the same TGA of these samples under nitrogen atmosphere, hardly showing any difference showing very little difference between Ppm Triazine containing and not TGM containing composites. The difference, however, it is to be noted that the thermal stability here is much more than in air. This is the structure, the stereochemistry responsible for the thermal stability in mill processing of plastics with Ppm Triazine. Ppm Triazine exists, we believe, in the boat form, and when exposed to heat, it exists in the tier form, and when exposed to heat, gets converted to boat form, thus absorbing heat and heat energy. Pathway to plastic management, endothermic incineration, and efficient energy extraction. Plastics are basically high-quality solid fuels. We should be fully utilizing their life cycle for the sake of sustainability. Thus, of all the alternatives available, the most logical procedure of their ultimate disposal is by incineration and energy extraction in closed systems. Incineration of any waste is particularly desired to prevent the occurrence and reoccurrence of infectious diseases. However, for safe, environmentally friendly, and efficient energy extraction, endothermic incineration is required. These objectives can best be achieved by imparting suitable incineration resistance to most plastics, not only for their ultimate safe disposal, but also for their safety while in use. To be noted is that much of the energy of combustion processes is lost in combustion gases, and hence the need for endothermic incineration. Ppm Triazine technology for fire resistance, and energy extraction. Here we have the example of polypropylene with and without Ppm Triazine. The peak heat release rate of polypropylene itself, when it burns, produces 800 kilowatts per square meter of heat, whereas the samples containing Ppm Triazine produce only 20% of the heat. The burning time is prolonged, almost double. That means the energy is better utilized, and most important, the smoke. There is very little smoke production, meaning that carbon emissions are very low. Future outlook. The knowledge and experience gained from endothermic incineration of plastics should be used in search of economical and cleaner combustion fuels, less emissions and lower combustion temperatures to arrest global warming. To be borne in mind should be that much of the energy of combustion processes is lost in combustion gases and not fully utilized fuels. For fire safety of electrical engineering storage devices, much more efficient fire resistance is required. Here, and even for space research, in situ ceramification technology of fire retardancy is perhaps a solution. The mechanisms proposed herein should also be used for the creation and the theoretical studies of new smart materials. This work has been done in collaboration with various universities worldwide. However, the opinions and interpretation of the results are entirely of the author himself. Thank you for listening.
Well, that concludes the session today. And please join me to thank all the speakers for the contribution. And thank you all for joining me in this difficult situation. And wish you a happy evening, morning, afternoon, depending where you are, and hope to see you in the future. Thank you.
Thank you, Dr. Tang. Thank you.
Thank you, Chi-Ching. Help us navigate all the difficulties.
A pleasure.
All right. So long.
Bye.